Thank you very much for being my wonderful TA as always. You are amazing and I couldn't do this without you. So pleased to have you here with us. Kat will be looking after the chat and looking after you guys. So if you've got any questions, please do post them in the chat and we will get to them. Okay, so before we start talking about functions and relationships, I wanted to just discuss with you the idea that there are connections between quantities in the world. So we're first going to look at some situations where there is no relationship, and then we're going to look at situations where there is a relationship between things. All right, so the first thing that we're looking at is the number of fingers on a person's hand. All right, so if you are 14 years old, and I suspect many of you this evening here with us would be, how many fingers does a person who's 14-year-old have typically? What's normal for a 14-year-old? Let's see if there's some hands up. Okay, Buhle, I see your hands up.
Yes, ma'am.
Yes, did you want to ask a question or do you want to tell me something? I
wanted to answer the question.
Sure, go for it. How many fingers does someone who's 14 have?
It's already been said in the chat, but I'm gonna say it anyways. It's 10. The 14-year-old has 10 fingers.
Has 10 fingers, absolutely. And in actual fact, if we want to be really particular here, we could say we have 8 fingers and 2 thumbs, because typically speaking, our thumbs are not fingers, but let's not go down that road. But yes, perfect, right, correct answer. Sorry, that was Buhle. Devin, how many fingers does a person who is 41 years old have?
They also have 10 fingers.
They also have 10 fingers. So now the question becomes, does the number of fingers on a person's hand depend on their age? What would we say in this situation? Let's see who's got a hand up. Motsebang, what would you say?
No, because there will still be 10. They will never change those 10.
Okay, so quite right. No, the number of persons on a number of fingers on a person's hand does not depend on their age, because it doesn't matter how old you are. All people are supposed to have 10 fingers. Okay, so irrespective of age. All people have 10
unless
fingers.
the fingers were cut off.
Yes, unless your fingers were cut off, or unless you were born with an extra finger, or unless you were born minus a finger, or whatever the case is. But the point is that there is no relationship between age and the number of fingers on our hand. Okay, there is no relationship there at all. Okay, so that's what they're saying over here, that the two quantities in the above situation, age and the number of fingers on a person's hand, are not related to one another. Okay, as age changes or varies, the number of fingers on a person's hand stays exactly the same. So now let's look at a few situations where one quantity influences the outcome of another quantity. All right, let's say if it does, how it will affect it. All right, and whether there is a constant in the situation. So in this example that I've given you here, all right, we would say that the number of fingers on our hands is what is constant, because that's never going to change. We're all going to have 10 fingers. Our age, however, is what changes, and that's why we call that the variable quantity. All right, so the word constant means that something has to stay the same. So whatever is the constant quantity, it stays the same. The age, or whatever varies or changes, is called the variable quantity. So that's the one that changes. Okay.
Ma'am, it would be 11.
I beg your pardon?
It would be 11, the number of calls you make and the amount of airtime left on your cell phone.
Okay. When you say 11, what do you mean? I don't understand.
I thought it asked the number, like the number, is it 11?
Okay, it's not 11. It's not 11. So it works like this, all right? The number of calls that you make and the amount of time left on your cell phone. All right. So what we've got to do is we've got to look and say, will one thing influence the other? So in other words, if you make more calls, what will happen to the airtime on your cell phone?
It will be reduced.
It would be reduced, absolutely. So in this situation here, I'm going to take Raitu, you had your hand up. Did you want to answer a question? You could answer this one if you want to. Maybe Raytu's been a little bit shy. Okay, so what we would say here is that as the number of calls increases, the amount of airtime on your cell phone decreases. So there's definitely some sort of relationship here, all right, because the number of calls that you make will influence the amount of airtime that you have on your cell phone. The more calls you make, the less airtime, all right? And similarly, if you made fewer calls, you would have more airtime on your cell phone. All right, the next thing, the number of houses to be built and the number of bricks required. Let's see who's got a hand up. Devin, you've got a hand up. What would happen here, Devin?
I don't know, ma'am.
Okay, that's fine. We'll take somebody else, not a problem. Tolana, your hand is up next. I hope I pronounced your name correctly. Kabisi, Tolana Kabisi.
The number of bricks will reduce.
Okay, so the number of houses to be built and the number of bricks required. So in other words, the more houses we build, the more bricks we're going to need. Isn't that true?
Yes.
Okay, so as the number of houses to be built increases, so the number of bricks will also increase. So what we've seen just in these two examples is that there can be a relationship between a quantity where one quantity increases and the other one decreases. Or there can be a relationship where one quantity increases and the other one increases. And now if we have a look at 2.3, it says the number of learners at school and the duration of the maths period.
I cannot see the writing in 2.2.
I can answer.
I'll make it bigger.
Thank you, ma'am.
Is that better? There we go. So as the number of houses to be built increases, so the number of bricks required would increase as well. Let me just put that in there. I didn't finish that off.
Ma'am. Ma'am.
Yes.
Can you please repeat the sentence of 2.2?
Okay, so they were talking about the number of houses to be built and the number of bricks that would be required to build these houses. So what I was saying was that as the number of houses to be built increases, so the number of bricks required would also increase. Okay, so the more houses you build, the more bricks you need.
Thank you, ma'am.
Okay, no problem. All right.
Excuse me, ma'am.
Yes, Nathaniel.
Is this right, ma'am?
Is this rate? No, we're not necessarily talking about rate. Rate does talk about relationship. Rate talks about the relationship between two things that are not the same. But we're actually going to be talking about functions and relationships, but we're going to talk about mathematical relationships. I just wanted to start with things that we use in our everyday lives and just establish that there are some things that have relationships and there are some things that don't.
Okay, ma'am. Thank you, ma'am.
Okay, all right. So now what about the number of learners at a school and the duration of a maths lesson? All right, Ray 2, do you want to answer that one, Ray 2?
Nope.
No, okay, that's fine. Let's find someone who does. Buhle, do you want to answer that question?
Yes, ma'am.
Okay, Buhle, what do you think?
Ma'am, I think it's the number of the duration of the math period, because a math period could be 1 hour or 2 hours.
But does the number of children at a school affect how long the maths lesson is going to be? I mean, in this lesson that we're having this evening, if we have 40 grade 7s or 20 grade 7s or 90 grade 7s, is it going to affect how long we're going to be sitting here talking for?
No.
No, absolutely. All right. So this is a situation where there is no relationship. Okay, there is no relationship between the number of learners at a school and how long the maths lesson is, just like this evening. Okay, so irrespective of whether there were 10 children at Watobe or 100 children at Watobe, our lesson would still be 1 hour long. Okay, so here, what we would say is that there's a constant and there is a variable quantity, okay, which we didn't see in the previous two questions. All right, in this particular question, the number of learners at the school would represent the variable quantity. And the duration of the maths lesson would represent the constant quantity. Okay, but here definitely not. The number of learners at school is not going to influence how long a lesson is. Okay, now see there's some more hands up. Pabalo, what did you want to ask something?
Yes, ma'am. Ma'am, I wanted to
Sure.
ask at 2.3. Ma'am, when you say the number of learners at a school and the duration of the maths period, ma'am, we have, let's say in a day, and there's only one maths teacher. Can't you say that she has to go to different teachers, different classes, and teach different amounts of kids, but all in a certain amount of time? So we have to cut time.
Absolutely. But what I'm saying is that if you consider how long one lesson is at a school, right? The number of children that you have at that school doesn't change how long the lesson is going to be. So it's just like us being here tonight at Watobe, whether there was 10 children in grade 7 that were coming to this lesson that I'm giving tonight, or whether there were 100 children, my lesson would still only be 1 hour long. Okay, so the number of children is not going to change the length of the lesson. All right, I know we can start thinking about all sorts of things. Well, what if there's one teacher and what if there are 2 children and whatever the case is, but we're not meant to be sort of looking at all those other sorts of things that would change it. It's just, it simply is that the number of children at a school would not affect how long a maths lesson or any lesson was for that matter. Okay, other things would affect the length of the lesson, but not the number of children at the school. Okay, all right. So if we have a look here, so if one variable quantity is influenced by another, then we can say that there is a relationship between the variables. So if one thing affects another, we can say there is a relationship between the two. And sometimes it's possible for us to find out the value of one quantity. In other words, what number is linked to a specific value of the other variable. So in other words, if I have so many of these, how many of those do I have? All right, so the number of the one affects the number of the other. Rachel, you put your hand up again. Do you want to ask something? Gerald, your hand's up. Do you want to ask something? Pabalo, your hand's up. Do you want to ask something?
Ma'am, may I please answer 3.1?
Sure.
Ma'am, it says how many yellow squares are there if there is only one red square?
Yes.
Ma'am, it would be 4 yellow squares.
Okay, so 4 yellow to 1 red.
Yes, ma'am.
Good, that's lovely. Thank you very much, Pabalo. And
Okay,
Tekelo,
ma'am.
do you want to answer question 3.2?
Yes, ma'am.
Go for it.
6 yellows. 2 reds.
That's it, to 2 reds. Well done, that's lovely.
Now
Zinhle.
can I answer 3.3?
No, no, no. Okay, my darling, there's no shouting out. We have to put our hands up so that
Sorry, ma'am.
everybody gets it. It's okay, so that everybody gets a turn. So the next person on the line here with hands up is Devon. Okay, Devon, how many yellow squares if there are 3 red?
There would be 8 yellow squares.
8 yellow squares. All right, so 8 yellow squares to 3 red. So would we say that there's a relationship here between the number of yellow squares and the number of red squares? Bonolo, what do you think? Is there a relationship between the number of red squares and the number of yellow squares?
Ma'am, I was raising my hand to answer.
Okay, all right. Well, then I'll call on you again later. All right. So in this situation, what we are seeing is that there must be some kind of relationship between them, because as the one changes, so the other one changes. What we notice is that when the red squares increase, the yellow squares increase as well. All right. So now let's have a look at a flow diagram, which is another way that we can represent a relationship between quantities. Okay, so I'm hoping that you're going to be able to see the connection between the arrangement above and our flow diagram. So because we can also describe our relationship between the red and the yellow square in terms of words. All right, so what we see here is that when we have one red square, all right, when we have one red square, we saw that we had 4 yellow squares. So now we can say to ourselves, well, 1 is going in and something is happening to it, and 4 is coming out. So in this particular rule, 1 is going in, we're timesing it by 2, and then we're adding 2 in order to get the number of yellow squares. Okay, so our input numbers are our red squares and our output numbers are our yellow squares. All right, so the next question is, if we wanted to get 6 yellow squares out, how many red squares would we need? Okay, Ranghuato, I hope I pronounced that correctly. How many red squares would we need?
2.
2. Let's have a look and see what's under here. Absolutely. Okay, well done, because 2 times 2 would give us 4, and 4 plus 2 gives us 6. Well done. That's perfect. Reitu, do you want to tell us how many yellow squares we'd have if we had 3 red ones?
Yes.
Sure. What would you have?
8.
Good job. Well done. There we go. All right. Buhle, your hand's up next. If we had 4 red squares, how many yellow squares would we have?
We would have 10.
We would have 10, absolutely. All right. And then the next person, into Kelo, if we had 5 red squares, how many yellow squares would we have? And Tekelo?
Would have 12.
We would have 12. Well done. Okay, so 5 went in. We operated on it by timesing by 2 and adding 2, and 12 came out. All right, so now if we repeat the same thing and we talk about what we're doing in words, we would say that the number of yellow squares is found by multiplying the number of red squares by 2 and then adding 2. So Devon, how many yellow squares will there be if there are 10 red squares? Devon?
22.
Okay, all right, so there would be 22. I mean, that wasn't Devon, but that doesn't matter. All right, so there would be 22, sorry, yellow squares. Okay, Tolana, Kabisi, how many yellow squares would there be if there were 21 red squares?
44.
44. Okay, now I'm going to ask a difficult question, all right? If there are 100 yellow squares, how many red squares are there? Let's see who's up next. Pabalo, if there are 100 yellow squares, how many red squares would there be?
Ma'am, it would be 202 because, ma'am, if there's 100 red squares on the top and the bottom, it's going to be the same number. And on the sides, there's only going to be 1. So that adds up to 202.
So that adds up to?
202.
202. Okay. Not such a difficult question after all. Now, no, hang on a second.
Lee, isn't it the other way around?
It's the other way around for this one. Hang on, it was the same.
Pretty close in the chat.
Pardon?
Lesedi in the chat is pretty close.
Okay. Yes, there we go. All right. Sorry, that's what I was trying to get at. I wasn't sure which one was the output and the input. I lost count. Okay, so now that unfortunately, Pabalo, is not the right answer to the question. Okay, because I have told you. Hang on a second. Did I do 3.5 and 3.6 wrong?
It's 48.
There's 10 red. 21, no, so that was perfect. Okay, so now here, all right, this is a different question, sorry. Okay, so if there are 100 yellow squares, how many red squares are there? So now we've got to be very careful about how the question has been asked. The 100 yellow squares represents the output. Okay, remember the number of red squares is what goes in. We operate on it by timesing by 2 and adding 2, and then we get the number of yellow squares out. So this question is different to 3.5 and 3.6 because I haven't given you the input. I've given you the output. All right, now let's have a look. There are a few people are saying all sorts of things here. So Lesedi said 48. Cornelia said 48. Asimatle said 49. 49, 40. Okay, so there's a few people with all sorts of different answers. Okay, so it's not a guess, guys. It's not a guess at all, right? We have to undo what's been done, all right? So in other words, we need to do the opposite, Okay, if a number goes in and we times by 2 and we add 2 and we get a number out, then if we take the number that comes out, we have to reverse these operations. So the first thing that we have to do is the opposite of plusing 2, which is to minus 2. And once we've finished plusing 2, we have to do the opposite of timesing by 2, which is dividing by 2. So that means that we now need to take our number 98 and we need to divide it by 2. What are we going to get in this case? We're going to end up with 40. Okay, we're going to end up with 49.
49.
That's it. Okay, we're going to end up with 49. So well done to everybody who said 49. Okay, does that make sense? You can pop something in the chat. Hold on, I'm just responding to the chat. What we can do is we can try another question if we want. Let's make this. What happens if there were 74 yellow squares? How many red squares would there be? Okay, so let's see what you guys put into the chat. It's okay, Devon. Exactly, you guys have got it now. Okay, so we would have to start with 74, take away 2, do the reverse process. That would give us 72, and then take 72 and halve it. Okay, there would be 36. Okay, so the point here is that there is a relationship, a mathematical relationship between the number of yellow squares and the number of red squares. And mathematicians are very interested when things form relationships, because then we can start looking for patterns. Okay, and what we do is we call these patterns, they've got a special name in maths, we call them functions. Right, so when you are studying functions, and it's a huge part of high school maths, we are looking at a mathematical relationship between two variables, and it's often represented as an equation. So for example, you might see something like this: y equals x plus 1. You've probably seen equations like that at school, and they've got you to substitute and to calculate inputs and outputs, etc., etc. All right, now I see there's some hands up. Is this just because you wanted to ask questions, or Raitu, do you want to ask a question?
No, I wanted to answer.
Okay, I'll call on you again. Zinhle, did you want to ask a question?
No, ma'am.
Okay, Tolana, did you want to ask a question?
Yes, ma'am. What does it mean when it says independent variable?
Okay, okay, all right. So it says interdependent. Okay, so are you talking about the green writing up at the top, or do you mean inside the green arrow?
The one in the green arrow.
Okay, so when we talk about a dependent and an independent variable, we are talking about one variable that basically the one changes in relation to the other. All right, so most of the time what we say is that the x variable is the one that's going to be independent. So let's take an example over here okay, when we were talking about with your airtime and the cell phone, okay? So if I draw a graph, and this is my horizontal axis called my y-axis, and this is my vertical axis called my y-axis, what I would do is I would plot time on the x-axis, okay? So 1, 2, however many minutes go past, 3, 4, 5, 6. Over here, okay, it's amount of airtime. So let's say we start off and we have 200 rands worth of airtime. That would be 100. That would be 50 rands worth of airtime, or whatever the case is. All right. So what I'm saying here is that if I don't talk on my phone at all, I'm going to start off with, for example, with 200 rands worth of airtime. Okay. But if I talk for however long, let's say I talk for 3 minutes, then the amount of my airtime has halved. All right. If I talk for another 3 minutes, then the amount of my airtime would decrease again. All right. So maybe what I should rather do is this. So let's say I talk for 1 minute or 2 minutes. I've got this. Let's just. And if I spoke for 4 minutes, I'd have that. And if I spoke for 6 minutes, let's say it's finished. All right, so what I'm seeing here is a relationship. Sorry, my dots are in the wrong place. What I'm seeing is that as the one thing increases, the other one decreases. So now time is what we would consider to be independent. And the amount of time that you have on your cell phone, or amount of airtime that you've got, would be considered the dependent variable. And it's very easy to figure out which one is the dependent variable and which one is the independent variable. Does the amount of airtime depend on time, or does time depend on the amount of airtime? So could you say, well, because 10 minutes have gone by, I've got 200 rands worth of airtime? No. But you can say, well, if I talk on my phone for 10 minutes, my airtime is going to decrease from 200 rand to 100 rand. So the amount of airtime you have depends on how long you speak for. Okay, so that's how you would know which one is dependent and which one is independent. Okay, and we 99.9% of the time, we put the independent variable on the x-axis, and the one that depends on the other one would go on the y-axis. Okay, does that answer your question?
Yes, ma'am.
Okay, all right. And then the other thing that we need to have a good understanding of, right, is this whole idea that the building blocks of functions are inputs and outputs. All right, so an input is any number or variable that a function or action, function or relation acts upon to produce a result. An output is the result of the operation on a mathematical object due to respective inputs. So in other words, we have the system of numbers, something that's being fed in, called your inputs, and something that comes out as a result. Okay, so in other words, when your input goes in, it's operated on by a rule or a relationship or a function, and it results in an output. Okay, one of the other ways that we can see this, all right, is with spider diagrams. Okay, so we're all familiar with those. I'm sure you guys have worked with spider diagrams at school, and it's just another way to represent mathematical relationships. All right, so the input numbers are the ones that are on the left, and the output numbers are the ones that are on the right. So now what I'm going to do, this is really quite easy. The next ones are a little bit more difficult. I would like you guys to do maybe, hang on a second. Here in A, this is going to be a little bit harder, all right? If we wanted to work out what this input number over here is, so here where I've put the little pink dot, Okay. What am I going to need to do to 3 in order to work out what that input is going to be? Okay, Ritu, go for it.
Ma'am, we're gonna have to say 3 minus 3,
Good.
which is gonna give us 0 times 2 will give us 0.
Good, lovely. So 0 must have gone in. All right, in order for us to get 3 out. Lovely. Okay, let's see who's next on the list. Zenhle, do you want to do the next one for us?
No, ma'am.
Yes, so the answer that you get out is the output. Okay, Tolana, that is quite right. Zenhle, you don't want to do the next one. That's fine. Devin, do you want to do the next one?
Which one, ma'am?
Okay, so what we've got to do here is we know that the output is 5. How are we going to work backwards to the input?
The input is 1.
The input is 1, absolutely. And how did you get that?
Ma'am, since we're going backwards, I took the 3 minus it by the 5 and it gave me 2. Then I divided 2 by 2, which gave me 1, ma'am.
Okay, absolutely. Okay, so that gave you 2 over here. No, hang on, sorry, I beg your pardon. It gave you 1 over here. That would be correct. Okay, 1 times 2 is 2 and 2 plus 3 gives us 5. Okay, the other questions are really quite simple. Okay, Buhle, what happens when 5 goes in? What do we get out?
5 times 2 is 10. Then plus it by 3 is 13.
Good, Buhle. Thank you very much for your lovely answer. Asimahle, do the next one. What happens when 9 goes in? What do we get out, Asimahle?
Awesome. Ma'am, you get 21.
Lovely, Asimahle. Well done. That's perfect. Good job. Okay, Lesedi, you're next. What do we get when 11 goes in, Lesedi?
Ma'am, we get, so 11 times 2, which is 22, plus 3, which will be 25.
Lovely, Lesedi. Beautifully put. I'm very impressed. Well done. Very nice. Good job, guys. That's nice. Okay, so now the other one was just very easy. That's just there for us to see what a spider diagram looks like. So now here is the challenge to you guys. All right, you've got A, B, C, and D. All right, you are going to work out the corresponding outputs. Okay, so you're going to do this quietly by yourselves, right?
Ma'am,
And when, yes, Gerald?
are we doing all of them?
I would like you to do all of them. I think it would be good practice for you.
Okay.
It shouldn't
Thank you,
take you too long.
Oh, thank you, ma'am.
Okay. All right, so you guys are going to use the input and then calculate the corresponding output. And then when you are finished all 4 questions, then you can say that you are done in the chat, okay?
Yeah.
She's gone.
Okay, remember to put your mic on mute. Thank you.
And A.
Wow, there's so many of you that are done already. Sure. That's very good. That's good. I'm glad this was easy. Okay, so let's go back up to the top here. All right, Lucy, what did you have when 2 went in question A?
I had 9.
You had 9. Okay, and what was the next value? When 3 went in, you had?
10.
Keep going.
11.
Uh-huh.
And 13.
13. Good job. Well done. Perfect. So that one was quite easy. Ranquato, you're going to do B for us. What happens when 3 goes in?
The answer is 15.
And then when 4 goes in?
The answer is 20.
The answer is 20. Good. And when 6 went in?
The answer is 30.
The answer is 30. Absolutely it is. Okay, Buhle,
Yes,
what happens when 1 goes in, Buhle?
it's 7, and then 12, and then 17, then 27, then 32.
Okay, so do you think that in question C, it's possible for one of the outputs to end with a number like 9?
Wait, let me just.
What do you think? Do you think it's possible for a number in the outputs in question C to end in a 9?
No,
No, why not?
ma'am. So let's say for question 3, we would need, for question 3, we would need to times it by, we would need to times it by 2, then add 3 to get to 9.
Ma'am?
Yeah,
D.
so it wouldn't be, yes?
Please double check the C by number 4.
It's supposed to be 22.
Sorry. Oh, sorry, that should be 22, shouldn't it?
Yes, ma'am.
There we go. That's better, isn't it? Okay, there we go. All right, so those all seem to be ending in 7s and 2s, so not likely that it's going to end in a 9. Okay, and then the person who was next was Lesedi. Okay, Lesedi, what would happen in question D? What would we get out?
It would be 5, 7, 9, 11, and 15.
Good job. All right, lovely. That was super easy, wasn't it? Okay. All right, now, do you remember how to calculate the rule? So in other words, if we had a look at pattern C, for example, okay, and we had a system of inputs, and 1 goes in, and 2 goes in, and 3 goes in, and 4 goes in, etc., etc., and then our outputs, which we call Tn in this case, and 7 comes out, and 12 comes out, and 17 comes out, and then 22 comes out. Do you remember how we found the rule? Okay, we were doing that in number patterns. So we would have said 12 minus 7 gives us 5. And 17 minus 12 also gives us 5. And 22 minus 17 also gives us 5. So because the first difference is constant, it means this has to be an arithmetic pattern. And if you recall, we would have taken that 5, multiplied it by our first input, but we don't get 5 out, we get 7 out. So we need to add 2 in order to get to 7. And we would repeat this process. So 5 times 2 plus 2, and that's where the 12 would come from. And that's why the nth term, the rule of the pattern, is going to be multiply by 5, multiply input by 5, and add 2. Okay, so let's see if you can work out what the rule is in this table to calculate the missing output numbers in this relationship. And then once we're done with that, then it's going to be time for you guys to go and do the poll.
Excuse me, ma'am.
Yes, Nathaniel?
Ma'am, in our school, ma'am, instead of putting the input and output numbers, ma'am, my teacher puts in X and Y, ma'am. Does it still make the same value or?
Absolutely, Nathaniel, absolutely. So whether we call the input numbers X and Y, or whether we call it N and TN, it means exactly the same thing. The difference is that when we're talking about this sort of notation over here that's on the left, okay, we are talking about number patterns specifically. So in other words, in order to create the first number pattern, the first term in the pattern, the number 1 has to go in for the first term. So there is a restriction on what n can be. N can only be counting numbers. But when it comes to input numbers that are used with an X, then your X can be an integer. So in other words, it can be 0, or it can be -1 or -2, and that's going to be more useful to us as structure. So whether you look at it in terms of X or Y, or N and TN, it really does mean the same thing at the end of the day. It's just that N has to be a counting number, whereas if we use X, then it can be an integer.
Yes, ma'am. Thank you, ma'am.
No problem. That's nice. So Devin says she knows the rule, and Bouchle says he knows the rule. Kanye is done. So is Bulela. And Favor. Sorry, Devin, did I call you a she? I beg your pardon. And Luna's done. Good, all right. So I'm going to ask, okay, Bouchle, what did you get the rule to be?
Ma'am, the rule for me, for number 1, at first, the rule I got was 7 times the output times the input plus 2. So it'll be so to get to the output of 3, I would do 7 times 3 plus 2, which gave me 23.
Absolutely. Absolutely. So whether we chose to write this rule as y equals 7x plus 2, or if we wrote it as tn equals, whoopsie daisy, not 2, if we wrote it as 7n plus 2, it really wouldn't have mattered in this case. All right. So who managed to get that right? You can say me in the chat if you did. Thanks, Stephen. Thanks, Luna. Oh, lots of you.
Yes, me.
Cool. Good job. Okay. All right. So then, Takalani, what did you get as your answer to go in here where number 4 is?
Ma'am, at number 4, I said 7.
Yes.
4 with the bracket plus 2, which is equals to 13.
It certainly is. Very good. Well done.
Thank you,
Okay.
ma'am.
Nice. Good job. Okay, we're almost finished. Kanya, what did you get when 5 goes in?
Ma'am, I got 57.
You got 27.
37.
37. So Tanya says that would be 30. Andrews. I think that's, who's Juanita? Oh, it's Jaden. Okay, Jaden. What did you get when 7 went in, Jaden? You got 44. Okay, so I'm not getting 44 because if 7 goes in and we times it by 7 and we plus 2, that would be 49 plus 2, which means we would get 51. Okay, and then the last person I'm going to call on today is Kwanda. Kwanda, what did you get when 10 went in, Kwanda? Oh, so Devin, answer the last one then, since Kwanda's not answering. Go for it, Devin.
Ma'am, I got 72.
You got 72. Devin, you are 100% correct. That's excellent. Well done. Okay, so now it's time for the